So our next speaker is Elliott Campbell, one of the workshop organizers as well. Elliott is apparently at UC Santa Cruz. Some big announcement for all of us. He was at Merced, I think. And he's been really pioneering a lot of the recent advances and analyses of OCS especially, or COS. We should just settle on the workshop of one. So otherwise we're going to waste a lot of breath space, going back and forth. And especially looking at satellites and, as Joe Barry showed, he's been looking at it for a long time, but a lot of new information has been coming out recently that Elliott has been pioneering and leading. And Elliott mostly publishes in Science and Nature, and every once in a while dips below, and we'll throw out a PNAS paper here and there. But he's definitely a brilliant scientist in our day, and let's welcome Elliott Campbell.
All right, thanks, Josh. Well, thanks everyone for making the trip and being here. I'm really excited about the week, and it's a tough act to follow, Joe Barry, of course. But I'm just amazed, not only a legendary scientist here, but how hip he can talk about this gas as COS or OCS. He's not confined by labels. And this is the kind of scientist we need today. So amazing, Joe. So I'm going to go into the carbonyl sulfide and talk about a few of our applications, including one that we're just really starting up right now. So this is some kind of very new stuff we're going to share with you. We haven't presented it before, but some old stuff too. So I'll start off with just a little bit along the lines of what Joe was talking about, the background, and I'll go through some applications at 3 different scales, mainly these larger regional, continental, and global scales. So before we talk about the new tracer, you might say, well, why do we need carbonyl sulfide? CO2 is taken up in photosynthesis. This is a pretty nice tracer we could work with if that's what you're interested in studying. And so Stephanie Vey's work on the DC-8 is shown here in black. The airplane flies around North America during the growing season, and so the y-axis here is altitude. The x-axis is the CO2 mixing ratio she was measuring. And you see this drawdown because the plants near the surface are taking it out of the atmosphere faster than it's being replenished from the, say, inflow from the oceans. And lo and behold, we model this just without any optimization, and it comes out pretty good. And so Joe showed you a spread of models earlier, and it looked like we have some major problems here. And you might look at this plot and say, gosh, no optimization. We're kind of right on the mark. This is looking very good. And one of the problems here is that we might be getting the right answer for the wrong reason. So I'm sorry this is kind of light, but this is that signal that Stephanie Vey measured. This is just the drawdown, the difference between the free troposphere and the boundary layer, around 5 parts per million, and then the model doing a pretty good job. But what lies beneath is, in the model, a very large photosynthesis signal, a piece of the model, and a very large respiration piece to it. And if we used the CASA model, but if you go to other models, you'll see a really wide spread, the kind of spread that Joe was showing, where you could have the photosynthesis and respiration be very small or even larger. But they all kind of balance out in a similar way to get you at about the right answer. And that's fine if all you're trying to do is interpret Stephanie's measurements in 2004. But if you want a predictive capability, if you want to be able to run this thing forward into the future and know how it'll interact with climate change and with different CO2 levels and land use, then you need to know these different model components separately. So you need another tracer. And you might say, well, wait a minute, another tracer? We don't need another tracer. We already do these really nice things with eddy flux towers where we can use the daytime and nighttime to separate photosynthesis and respiration with just one measurement, with just CO2 and maybe temperature or something. The problem is at these larger scales, when you're using remote sensing or an airplane and trying to understand maybe continental or larger scale, regional scale fluxes, that day and night signal is mixed up by atmospheric mixing at these larger scales. So for example, we could rerun our model, these model components, just averaging out instead of having hourly variation or whatever it was in the model in this case, just completely averaging out the day and night, and we get a similar result. So at the small scale, you do have some options, and maybe they're not ideal, and I think there are people in this room that are actually using COS to do even better work at the small scale. But at the larger scale, we have no option. We're really stuck. And that's a big problem, because that larger scale is one of the most important areas for applications, for trying to refine our global climate and ecosystem models. Okay, so then that's where carbonyl sulfide comes in. Instead of having these two large offsetting fluxes, at a regional or continental scale, it appears to be dominated mostly by an uptake mechanism by plants that can be related to that photosynthetic uptake of carbon. And so here again is that vertical profile. Now the observations for carbonyl sulfide are on the right from Nicola Blake and her group at UC Irvine. And the model does a pretty good job without optimization there. But unlike in the case of CO2, where we had these two large offsetting components, with carbonyl sulfide, to the best of our knowledge, at this large scale, this continental scale, the plant uptake was the most significant thing going on. The influence from an anthropogenic source, from soils, from boundary condition variation, at this regional North American scale that we were working on, are relatively small.
What is the two separate GBP and NPP components there?
Yeah, that's a good question. Thanks for asking. This was at a time when Jürgen Kesselmeyer's group had basically radically changed how big we thought the global carbonyl sulfide plant uptake was. And using his methods, we get this COS plant uptake. Using the older approach of scaling to NPP, we get this much smaller. I was actually close to publishing a paper that says, we have no idea why there's this large uptake over North America, and it was at AGU, and Peter Tans walked by, and he's like, "Oh yeah, you should read this new paper that just came out from Kesselmeyer's group, because it will really change the story probably." And we went back and did new model runs, and things came out looking pretty good. So anyhow, yeah, a lot as Josh.
Is there a component of COS exchange that's due to NPP independent of GPP? Is that what that's?
What's that?
Is there a component of COS exchange that is due to some aspect of NPP that's independent of GPP, or different? Is that what that's representing, or?
I think well, there's a couple there's a couple of changes in the older modeling approach. One of them is scaling by GPP instead of NPP, which is about a factor of 2. One of them is not having a kind of relative uptake that enhances how much COS is taken up on a relative basis to CO2. Those were two of the big changes. And a third change was just the ecosystem model people had been using previously had very small levels overall of primary production. So there were three basic changes. And the reason that is how it was done previously was, I think, just a mistake that people mixed up those two terms. So gross primary production is the carbon taken up during photosynthesis, and then net primary production would be the difference between the carbon taken up during photosynthesis and that released by plants in respiration. Yeah. But yeah, Jürgen Kesselmeyer's group, it's a Sandoval-Soto paper in Biogeosciences. Okay, and so it's not just at the continent. Joe showed this plot too, but we have these the seasonal amplitude as well in the northern hemisphere, or the higher latitudes in the northern hemisphere. You get an amplitude in COS and one in CO2, but we've plotted these y-axes on a sort of relative basis, and it's about a factor of 6 bigger. With the seasonality, same with this drawdown. If you do this on sort of a relative basis, it's about a factor of 6 bigger. So you see this show up in multiple places. And so you might say, okay, well, at the continent, you've got all this COS going into the land. Where is it coming from? And so we have done a review of global sources and sinks of carbonyl sulfide. Some of the sources are indirect, so other chemicals are emitted and then oxidized to COS in the atmosphere. But our review of the kind of range of estimates that have been made shows that the oceans could be quite large. Maybe industrial emissions could be pretty large too. On the sink side, the daytime plant uptake that's related to GPP seems to be the largest. And why this worked at a continental scale is, even though we didn't have a great handle on the oceans, there were measurements at sort of the inflow to the North American continent. And using those measurements, instead of really descriptive information of the oceans, we could kind of constrain what's coming into the land. And I think that's one of the reasons that Joe was pointing out that regional applications are a pretty exciting way forward right now. This is all evolving, though. We're learning lots of new things thanks to the new instrumentation. The people in this room, Rosine and Uli, have discovered some hot spots where this isn't the case in a certain time, in a certain location. But these larger scales, the global and continental case, the reason why we get these consistent patterns from the more background and larger scale measurements is because our a priori knowledge of the global sources and sinks shows that we've got a big plant uptake and a big ocean and maybe industrial input. Most of this industrial input, though, according to our inventories that have come out over the last few years, is from China. So again, if you're looking at a regional application in North America, where most of the measurements are being made, this could still be a tractable path. Here's the view from space. Again, I don't know if we're looking at a factor of 6 or what, but this is the mid-troposphere or upper troposphere from the MIPOS satellite from, Jim, do you remember what this was? Is this GOSAT? Sorry to put you on the spot. I'm forgetting. We made this a while back, but or Jim made this a while back. But what you see is this really dramatic drawdown in the upper troposphere over the Amazon, where you have convective transport, and you also have this large net uptake. In the case of CO2, the same transport processes should apply, but you've got this balancing between a large source from the ecosystem and a large sink, and so you don't get that same pattern. Another thing that's really evident in these maps are the source, and you saw this in the animation Joe was showing too, coming possibly from the tropics, maybe outflow from the Asian continent too, so two possible distant sources. Okay, so we have a perspective piece in EOS now. I think this is one of the things on the wiki that we're sharing. In this, we try and make summarize the argument for why this would be exciting to keep moving forward with more monitoring and more remote sensing for applications at the large scale. And the three key reasons we identified here were, at the continental scale, the real benefit is that this large spatial separation between the major source, which would be maybe the tropical oceans or industry in Asia, and the sink plant uptake allows you to use that spatial and temporal variation of COS to understand the plants better. In the higher latitudes, the extra beyond north of the tropics in the northern hemisphere, we've got this nice seasonality that seems to be driven by plant uptake and not seasonal variation in the oceans or seasonal variation in the anthropogenic. that should say northern extratropics there. And then for global applications, we have carbonyl sulfide sort of hitting the sweet spot for having a long enough lifetime that when it's emitted or taken up in different quantities, you see the signal throughout the global atmosphere, but relatively little buffering capacity, unlike CO2. Okay, so those are, that's kind of the argument for why we're excited about this tracer. And now I'll share a couple applications. And the first is work led by Tim Hilton, and he'll have a poster coming up too to describe this in a lot more detail. And what Tim was doing is really focusing on North America. It's where we have the most measurements. NOAA has airborne monitoring at a dozen or so sites, tall towers, and now we have this detailed eddy flux information coming out of North America too. And what we're showing here these aren't measurements, these are models, different models of this CO2 uptake during photosynthesis, the GPP. And you see really different spatial patterns here, right? Depending on which model you use, it's not just the magnitude, we have a small signal or a large, but just kind of a more evenly spread variation, concentration in the southeastern part of the continent, or a really kind of corn belt hotspot type of model. And then the next step is really to translate this simulation of GPP into what that might look like in terms of plant uptake of carbonyl sulfide. And so for each of these models, there's a couple different ways, as you can imagine, to translate a CO2 uptake into a carbonyl sulfide uptake. For example, Joe showed Karen Stimler's plot that showed this variation with light. At low light levels, you have a higher rate of COS uptake relative to CO2, and then maybe it stabilizes as it gets larger. So a more mechanistic way to translate from CO2 to COS would account for something like that. A simpler way is just to take sort of the day or monthly kind of climatological average, just a single number of what that normalized relationship is between the plant uptake of COS and CO2. Anyhow, we looked at a number of different ways to translate from CO2 to COS. And then this is what's happening at the surface, this kind of surface flux. But then we put this into an atmospheric transport model that then blows this around in a three-dimensional time-varying model space. And you can see what's plotted here then is the result of that atmospheric transport model. We're plotting the drawdown. Again, kind of what the airplane platforms see as they run these vertical profiles. And the drawdown here is on the order of 50 parts per trillion, so about 10% reduction in carbonyl sulfide between the top of the atmosphere and near the top of the troposphere and near the boundary layer. And then the next step is really to compare this to measurements, and Tim's poster will go into more detail, but if we look at these three categories, this sort of evenly spread GPP across the continent, that's more concentrated in the southeast, something that's more of a kind of agriculture, corn belt focused model. If you compare that with models, you get this result. So here we have the COS drawdown on the y-axis. On the x-axis, there are three different airborne sites. So NOAA has these three sites along the east coast, and as the air moves across, you see a pretty clear drawdown signal at three sites along the east coast, from the north to the central to the south. So something greater than 10% drawdown, and then so on as you get further to the south. And if you start with the model case that kind of spreads things more or less a little bit more evenly across the continent, you do a pretty good job. That's what's shown in blue here. Maybe not quite getting enough uptake at this northernmost site. It's kind of the outflow, the vent of North America as the air moves across. If you take the scenario where we put all the activity in the southeast, you do pretty well up north, but then you really overshoot things in the southern site. You don't see this much drawdown in the observations from NOAA on the southern site. And the green case here, where we kind of clump things more in the Midwest, that maybe is the just right scenario. The bars here represent a number of different treatments for these other sources and sinks. What different assumptions about what the soils are doing, they can be emitting or taking up, different assumptions about what anthropogenic sources are in North America. But even accounting for the different scenarios that we could find for those other sources and sinks, it looks like you can pretty clearly distinguish at least between these three cases. And so one of the key results from this paper, I think, is that we don't need a perfect tracer because there's a lot of uncertainty in our knowledge of the carbon budgets of North America. We just need something that's known better than GPP. And in this case, our present state of knowledge on COS seems to be telling us at least that this scenario of putting everything in the southeast is not going to be the right way forward. And that's our continental scale application. Yeah.
That top panel row those are different scenarios, right? I mean, they're labeled as different models, but you describe them verbally as just different scenarios for the uptake.
Yeah, these are different plant uptake models, and then the bars here represent more than just the plant uptake, also different assumptions about anthropogenic soil boundary conditions.
Right, but the three colors are the three models, and the three positions along the x-axis are the three different scenarios for uptake.
Oh, I'm sorry. These three positions here are for three locations where three different airborne profiles are flown once or twice a month by NOAA. So the northern is in, is it New Hampshire?
Yeah.
New Hampshire. Central?
Cape May, New Jersey.
New Jersey.
Southern side is
South
South Carolina.
Carolina.
Maybe I misinterpreted. I thought I was reading this as three different scenarios that were tested with three different models, and it looks like the green model, CASA, does well in all scenarios, and the other two diverge in between.
Yeah. Yeah. So we looked at the three different models. Sorry, I'm mixing up the word scenario and models maybe. The CASA model was the base of a bunch of different scenarios that are shown in green here. And those would include different assumptions about how we convert from CASAs in PP to a COS plant uptake, how we add on different sources and sinks that are also at the continental level besides just the plant uptake.
Does CASA do better because it's a different type of model? It's a diagnostic instead of prognostic model. It gets a lot of cheating from actual observations.
Yeah, yeah. And I think they did extra cheating for this specific case, because if you look a few years back, CASA doesn't have a hot spot in the Corn Belt. But and maybe someone can correct me, I wouldn't know specifically, but I'm pretty sure Jim Collette said that they took corn yields out of the Midwest and really cranked things up. So it's not just the satellites, it's yeah. And that's not to say yeah, so there isn't this in this case we don't have a way really to project forward as well, since the model's based on this type of information, corn yields and satellites. But it is kind of nice that the model that you would expect to do the best ended up doing the best in the comparison. The other thing that's really neat and really important for this conference is that it seems like SIF is telling the same story too. So there's continental analyses of SIF that also suggests that a spatial distribution like this is not nearly as accurate as something like that. And I'm not trying to pick on SIB because I know there's versions of SIB that'll concentrate GPP in the Midwest too. This just happened to be the version we were working with this specific paper. There's dozens and dozens of models out there, and these are three classes of kind of spatial variation that we did see in the different models. So CLM is another model that'll put a highly concentrated plant uptake in the southeast. Yeah.
It's interesting that all three models show reduced drawdown at the southern site, but cannabis actually in the model shows a higher GPP in the southern region. So I'm wondering what's driving that decreased drawdown in cannabis in the southern site.
So cannabis, maybe I'm misunderstanding. Cannabis doesn't decrease the drawdown very much. It still has a lot of plant uptake in the southeast, so it has a strong drawdown of COS. It's pulling a lot of.
Okay, I'm looking at that invert. Okay, so
Yeah.
I guess my next question would be, why do SIB and CASA show decreased drawdown in the southeast, even though they have no strong GPP in the southeast?
Oh, okay. Yeah, so if you have a lot of strong amount of GPP in the southeast, then you pull a lot of COS out of the air, and you get a strong drawdown signal. So yeah, maybe we should flip this y-axis, and that would be a better way to look at it. But the further you are, the higher you are on this y-axis, the more COS you're removing from the atmosphere, the more drawdown there is, and the more the model would do that if you put more GPP in the southeast.
I guess I just don't know why SIB and CASA are also showing decreased drawdown without high GPP in the southeast.
Ye-
Is it the transport model results that are driving the drawdown that's plotted there? So there is increased drawdown in the southeastern cannabis relative to the other two models, but these are also showing the transported air.
That's just the background.
From all the way across North America going west, so it's not only the local area that's influencing what you see in those drawdown plots.
Okay. But they do show less uptake in those other models.
Yeah, it's just 20 part per trillion drawdown. So a few % difference between the free troposphere and the boundary layer when we use SIB and CASA to drive the atmospheric transport model. Yeah. Yeah. Okay, so the northern extratropics, this is the new stuff. So this isn't our new stuff. This is Heather Graven's work. Lots of people have looked at this seasonal amplitude. I guess the flying carpet was a great one to look further back in Inez Feng's work. But one of the things that you see is a long-term change in that seasonality. What Heather and her colleagues have plotted here for Mauna Loa and Barrow, two background sites for observing CO2 and COS, is that in the earlier years, so in the 60s, here in black, you see a smaller amplitude than more recently. In the most recent, the pink observations, the amplitude increases. And there's a number of ideas about why this might be happening, but as you saw in the continental case there, you have different things influencing the CO2 signal, and respiration and photosynthesis are both in play. So if you want to try and interpret this, which a number of studies have been trying to do, right now you're mostly using models, but an observational technique would probably be to look at this long-term record in carbonyl sulfide. And so right now our results are, working with Yuting and others, are qualitative, I'd say, because we haven't incorporated all these other sources and sinks. But just looking at the total column measurements at Mauna Loa, which are much more frequent than the NOAA measurements. So a NOAA site will make maybe 20, 50 measurements a year. These total column measurements from the spectrometer can be hundreds or even thousands of measurements. And the seasonality at Mauna Loa appears to be growing. Nyalesund and much further to the north only gives you part of the year, but the seasonality here also appears to have some growth. The NOAA data at this point are just too noisy for us to work with because there's so few measurements, but this appears to be a fruitful direction to push forward if we can interpret what the change in the seasonality of GPP might be in these northern high latitudes from these long-term data sets, then we can have a better ability to interpret what we're seeing in the CO2. Now, this is only a relatively small piece of the global carbon budget, though, because again, Joe showed you this plot with this massive explosion in the tropics of not only uncertainty, but the magnitude in GPP. So we're also interested in larger scale, global scale applications. And thankfully, we have some really nice trends coming out of global scale measurement from Antarctic ice cores and firn air. So Steve Monska, Murat Aydin, and Eric Saltzman and others have been working on this data, and they see this pretty steady levels of COS concentrations from the Antarctic data, and then a rapid rise, and then followed by some decline, and then this last period here is this just more recent orange period where NOAA started monitoring this data at their global network. And so you can look also at some of the total column measurements, and they show some of the same trends. That's what we've just overlapped here. And when you look at this, probably the first thing you think about is anthropogenic sources. And so our first attempts to interpret this data were based on kind of going back to the anthropogenic inventories, pulling out all the information we could get from economic data, tracking some of the key industries that are related to the anthropogenic emissions. And when we put those into again, this is the global inventory. These are some of these anthropogenic inventories, aluminum, rayon, coal, there's others too. And then tracking the historical changes in the ocean source and plant uptake. You can see there's a number of sources of variability. When we put these scenarios into a model, this is the result we get, these green lines here. The black, again, is the work from NOAA and UC Irvine to track what's happening in the Antarctic ice and firn. And our first step in modeling really is doing something quite simple. There's a huge uncertainty in the plant sink and the ocean source. So you can't run a model without balancing these two, right? If you pick one that's low and the other's high, your model explodes. If you pick, otherwise, all the COS disappears if you pick a plant sink that's too big. So the simplest thing you can do is pick at random, more or less, from the distribution for the magnitudes and the temporal scenarios for all of these sources and sinks, and then pick an ocean sink, not at random, but one that, an ocean source, not at random, but one that balances out those other sources and sinks, just so you have a stable model scenario. And so when we do that, we get something that's somewhat reasonable. That's the green here, is the spread of models is really large because, again, we're picking at random from all those sources and sinks except for the ocean. But you can see there's a lot of room for improvement. And so we started to explore the behavior of the model by doing sensitivity studies to see which of the variables in the model, there's several dozen here, are most important in determining the agreement with this historical trend. And so in this case, we looked at a number of scenarios where we really kept the historical growth and the plant uptake to sort of the minimum range of what you might expect from global ecosystem models. That turned out to be one of the most sensitive parameters in the model. And then we turned up or down the anthropogenic source. And we could do a pretty good job. We could kind of line things up and improve over just this bigger spread and reduce the root mean square error a bit. I think we were at 11.5 here, and we get down to 10 there. We tried another set of runs here where we go to the maximum end of the range for how much GPP has grown historically from these global ecosystem models. Historically, the high end of the range is like 35% growth or so. And now we set that as the historical change, essentially, in the plant uptake. We look at, again, these different possibilities for the anthropogenic source. Could be large, could be small. And in this case, we actually end up getting a much better agreement with the observed trends. Not perfect. We're missing something there probably. Maybe we're growing too fast here, but much better. And this was just a way to sort of explore how the model's working. But when we went back in and we just tried, now instead of optimizing just a few parameters, if we tried optimizing all of them, okay, so we have all kinds of soils and atmospheric oxidation, and a wide range of sources and sinks. If we optimize all of them except for this historical growth in GPP, this is sort of the spread of error we get in the model. But if we optimize all parameters, if we let that GPP, how GPP is changing historically, be optimized as well, that really brings the model error down and shows us that how important the global growth in GPP is to getting a good fit. And it's incredibly important because we have this wide range of possible scenarios for how GPP may have changed over the last 100 years. The case where we reduce the COS model error the most is near the high end of those global scenarios. These are just ones that we added on that no one's ever actually put into a global model. Okay, so that's it for us. I just wanted to leave this last plot on just to remind you. I think one of the key aspects of this workshop is that, moving forward, the Amazon is where the largest uncertainty is, and it's where it seems like a good place for this integration of SIF and carbonyl sulfide could occur. Thank you.